So let me start with vectors. We review simple vector algebra, and what we need usually in this course, we just need to have skills how to find components. If you have a vector A, you can decompose it. You can find components, x component and y component. So it's pretty much at this point you just need to remember properties of right triangles. That's it, right? So right triangle, in order to find this component which is adjacent to the given angle, of course you need to use cosine function. Of course you need to remember when to use cosine and sine, but also in the formula sheet that information is given. So there will be a small triangle and when to use sine and when to use cosine. So a cosine, and of course y component, which is opposite to the given angle, of course it will be sine, a sine theta. Then, for the sake of convenience, in mathematics we introduce these unit vectors, I hat and j hat, positive direction of x-axis and positive direction of the y-axis. And of course, using these hat vectors, unit vectors, we can write nicely vector itself. A equals ax I hat plus ay j hat. Then, if you have a component vectors presented in a component form, adding, subtracting, multiplying them by numbers, it's a very, very simple procedure. If you want, for example, add or subtract vectors presented in a component form, you just need to add or subtract corresponding components, multiply by the corresponding unit vector, and that's it. Right? So it's very, very simple procedure. A little bit tedious if you have many vectors, but not complicated. So we're going to practice. We're going to look at one problem. Then we started learning how to describe translational motion, simple one-dimensional translational motion. And first, we introduced some simple vocabulary, words, quantities, which we need to use in order to describe fully one-dimensional system, moving along a straight line. So we introduce, of course, x, position, right? Then we introduce velocity, which is essentially derivative of the position as a function of time. And then if you are interested in the acceleration, of course, you need to differentiate velocity with respect to time. 3 levels: position, velocity, acceleration level, all the time. And it turns out that these 3 levels are enough in order to describe completely motion of any classical mechanical system. So then, it's a mathematical process of finding these kinematic parameters. Now, graphically, if you have a graph x versus t, you see this blue line. So then if you want to find information about the velocity at any point, you just need to draw a tangent line, or imagine drawing a tangent line, and slope of that tangent line gives you a velocity. So if slope positive, velocity is positive. If curve is sort of like this, slope is negative, then of course velocity is negative. So using this, you can plot velocity versus time. And for example, in this case, it's approximately will be something like this. First velocity increases and then velocity decreases, being positive at the same time. So then if you want to get acceleration, again, the same procedure. Imagine a tangent line. A slope of that tangent line gives you information about the acceleration. In this case, slope is constant up to this point, and it's positive. So positive constant acceleration. Then slope of that curve, of this part of the curve, negative and constant. So acceleration is constant. Right. OK, so then after this, we decided, OK, so now we know how we can describe any translational motion. Now, the goal of classical mechanics, predict the future of any classical mechanical system. And we started predicting the future of any system using these kinematic equations, restricting ourselves very significantly. We can use that only when accelerations are constant. Again, it's an introductory level course, so it's a reasonable level. So first equation, kinematic equations, again, which we derived, essentially it allows us to predict the future of the velocity. Then the second equation allows us to predict the future of the position. And these equations should be theoretically enough in order to predict the future of any classical mechanical system. But sometimes when time is not given, so this equation also useful. We just combine these 2 equations, eliminate time, and we ended up with this no time equation. Again, usually when it is useful, if you see in the problem no information about the time, question is not about time, it's usually a clear indication that this equation will be the most convenient probably to solve that particular problem. OK, and in these equations, of course, we assume that initial moment of time is 0. Right? It's reasonable, quite often this is the case. So then, after introducing this, so we decided to apply them to describe any projectile motion. Projectile motion, if you drop the ball, if you throw the ball near the surface of the Earth, any object, that is essentially projectile motion. So in this case, well, of course, we can decompose motion into two one-dimensional motions, motion along the x-axis, motion along the y-axis. And for the motion along the y-axis, we have to be careful in terms of acceleration, right? So if you choose y-axis upward and acceleration due to gravity downward, so this direction is negative relative to the positive chosen positive direction. In this case, acceleration in this equation is minus g, right? If you picked y-axis downward, then this g is in the direction of in the positive direction of y, then of course acceleration is positive, right? Then in the x direction, we assume that there is no air resistance. We can neglect that in the first order of approximation, right? So acceleration constant, we can use kinematic equations. So for the x motion, since acceleration is negative, so we're getting only one equation which allows us to predict the future of the position, and x component of the velocity stays the same throughout the whole motion. We just need to remember that, and I will keep reminding you about that when we start solving the problems. And in the y direction, nothing can be done. We just need to replace a with plus minus g, depending on the situation. And so all three equations at our disposal, we can use them, right? So we're going to solve a couple of problems about this. And so after this, now we can say we can describe and predict the future of translational motion, but there is another ubiquitous motion, rotational. So we also decided to describe that. Also, first, kinematic parameters, but now angular kinematic quantities, and then rotational kinematic equations. Philosophy is very similar. So let's assume that you have some point which is spinning or moving, rotating along a circle. So of course you can describe it using x and y like in the previous cases, but it's much more convenient to switch to r and theta. R, it's a distance from the axis of rotation to the point where the point is. In this case, it's a radius. And theta. R is constant, so pretty much the whole description will be in theta, description of the motion. So theta, angle, in this case, essentially it's like a position. And angle can be measured in degrees. It can be measured in number of revolutions, or it can be measured in radians. We introduce radians. Radians, if you want to measure this angle in radians, what do you need to do? You just need to take arc length and divide it by the radius. Right. So then, if you want to know how fast angle is changing in time, you just need to differentiate, and that's what, by definition, the angular velocity is, how fast angle changes in time. So d theta over dt, angular velocity. And this angular velocity can be positive, is positive, when object is spinning in counterclockwise direction, and negative when it's spinning in clockwise direction. Right? And the last thing, quite often we also want to know how fast the angular velocity changes in time. So that leads us to the angular acceleration, right? So derivative of omega with respect to time. And so these tools we need to describe the rotational motion, and then if we want to predict the future, where the system is going to be and what the system is going to do, similar kinematic equations. We just need to replace v with omega, a with alpha, and x with theta. Otherwise, exactly the same sounds. Too strong, similar equations. So pretty much that's the scope of the exam. So it's all about kinematics, translational kinematics, rotational kinematics. And from the next class, we will start discussing Newton's laws. We will start talking about dynamics. But first, we wanted to learn how to describe just a motion. All right? Okay, so now let me move the camera to the main position, and then the rest will be over there. Problem number 1. Right. So let's assume that we have what? Object, a car. And there are 3 vectors describing displacement of that car. First, it moved in one direction over some distance, then in a different direction over some distance, then another leg of the trip, and then we need to find the net displacement of the whole trip. So there are three vectors. Essentially, we just need to add them up in order to find the net displacement of the car between the initial and the final point. All right, so now I'm going to deal with vectors. Of course, first of all, I will introduce the coordinate system. Right? I need to introduce coordinate system, and then I will be able to draw them nicely. Okay. Okay, let me write vectors. And okay, let me estimate time space. So this will be my y-axis, and let it be over here, x-axis. On purpose, x-axis slightly elevated because most of the stuff is going to be in the fourth quarter. So the first vector, let me use black. So vector d1. d1, right, along the x-axis. Okay, I'm going to write its magnitude. Let me first show all the vectors on the pictures, and then I will start writing what are the numbers. Then the second vector is somewhat in this direction, d2. And this angle is 30 degrees between the x-axis and the vector d2. Then vector d3, and again, it's all displacements of the car. So first car drove this way, then turned slightly, moved that way. And the last leg is somewhat this way. Right, so this will be d3, and the angle which is given, this angle is 60 degrees. Again, between the horizontal line, essentially between x-axis, right, and this vector. In this vector. So graphically, where is the net displacement of the whole car? You remember displacement? It's like a boss's attitude. It doesn't care where the object was. It just wants to know where it was at the very beginning and where it is at the very end. So we just need to draw a vector connecting the initial point and the final point. That's it. You remember the property of a displacement. So essentially, this is our final vector, which I labeled D. So net displacement. Net displacement. NET, net. Right? So we need to find this net displacement. If magnitude of D1 is given, let me write that down. A magnitude of D1. You see, I didn't write the vector on top, so usually it means a magnitude, right? Or you can write it like this, D1 vector, but sign of an absolute value. What's the number? 620 meters. Then D2, 440 meters, and angles are shown on the picture. And then D3, 550. I'm surprised. Why didn't they do for symmetry 660, 440, 550? I don't remember where I picked this problem. Okay, yeah, so pretty much everything that we need is given, and now what we need to find? We need to find D. And you see, I wrote it as a vector. So we need to find essentially components. And once we will find components, we will find the magnitude and direction of that vector. So what are the steps? Of course, we need to write all these vectors in the component form, in their component form. And then once we do this, then adding three vectors is just a piece of cake. Add corresponding components, x components, and add y components. That's it. And then, of course, we will have to find the magnitude and direction. And I think we know how to do that. Right? So now find components. So first vector, which way labeled? I just put a bullet, a new bullet, yeah. So d1x and d1y. Y component of the vector, without thinking, what's the y component of the vector d1? Of course 0, because it's fully in the x direction, so obviously 0, right? You see? So 0. And then, of course, this magnitude is in the x direction. So x component 620 meters. Okay, so now, of course, I can write it in this nice form using I hat and j hat. So let me do it. So d1 can be written as 620 I hat plus 0 j hat. Okay, so now we prepared the first ingredient. So first we prepare ingredients, and then when ingredients are ready, we can start cooking, right? So just drop ingredients in the right order. So now second vector, d2, d2x, and of course d2y. Okay, d2 vector is over there. Guys, if you're not comfortable finding components when the vector is not at the origin, you remember properties of a vector? If you preserve, I have markers everywhere. If you preserve the magnitude and direction of the vector, you can move it anywhere you want, anywhere your soul desires. You can take it home, you can keep it here, right? So anywhere. So if you're not comfortable with d2 over there, just move it, displace it, and position it at the origin. But of course, at this level, you should be comfortable finding components. It doesn't matter where that vector is, right? But again, keep direction and magnitude the same. So x component of this vector, it will be obviously this, right? And y component will be that. So in order to find x component, let me write, so it's a d2x. Which function do we have to use? Cosine, because we need to find adjacent side adjacent to the given angle. So cosine function must be used. Again, remember that. And lots of students still struggle with that. Even in physics 2, still some students. But I will keep bugging you until you will remember that. So d2 magnitude and times cosine of 30 degrees. Component, positive or negative? Positive, because here you see this component, if you project it, you see it's this vector somewhat in a positive x direction. So this component is positive. Because again, we're not using conventional angle, we're using convenient angle. Conventional angle would be this one, so which will be 330 right degrees. So it's too much. I don't like those angles. So positive, and of course you can plug numbers, 440. Cosine of 30 degrees is the square root of 3 over 2. It's too much. I will look at my notes. All right, 381 meters, of course, right. Okay. So then, y component, of course, d2 times sine of 30 degrees. Sine of 30 degrees, I remember by heart. It's 1 over 2.5. This component, positive or negative? This one is negative, because you see, this component will point in the negative y direction. Points in the negative y direction. So, and again, since we're not using conventional angle, that minus is not going to pop up from cosine function, never. We use convenient angle, not conventional. So we need to take care of that plus and minus manually. Minus. And of course, yeah, I can calculate this. 440 divided by 2, it will be 220. So 220 degrees, right? Okay. Still, let me check if I am correct. Yeah. So now again, let me write in a nice form using I hat, j hat, because I'm just trying to brainwash you to write things in the right way. So d2, it will be 381 I hat. Minus. I said minus, and here I was so happy that I can calculate, and I didn't write the minus. minus 220, right? Minus 220. So minus 220 j hat. Right. Okay, so that's our first vector. Now the second vector. And now the last one, the third bullet. So d3x and d3y. X component, obviously it's this. Again, cosine function must be used because we are trying to find the side which is adjacent to the angle. You see, 60 degrees, and this side is adjacent. So cosine function must be used. And positive or negative? Negative, right? Because again, this component is in negative x direction, right? Is in the negative x direction. So it's and again, we're using convenient angle, not conventional. So we need to take care of those pluses and minuses manually. So minus d3 times cosine of 60 degrees. Right. Again, if somebody is not convenient or comfortable with these pluses and minuses, yeah, we can talk more about that. But I think we discussed in our recitation classes, and now we're just reviewing. Now I remember what I wanted to tell you at the very beginning, another thing, before you started saying. And again, it flew away. Such a subtle, no, simple, subtle, but every time it flies away from my head. Right. Okay. During the exam review session, I'm not trying to give you something fancy, something cool, right? No, we're just reviewing stuff which we just covered, right? So problems will be very similar to our recitation class problems or your homework problems. So don't expect something fancy. So then y component. Of course, it's this. And again, negative, right? Negative. So it will be minus d3 times sine of 60 degrees. I didn't write the answer. So now let me write that. So this will be minus 275 meters. Cosine of 60 degrees, again, it's a 1 over 2.5. And this d3, 550, yeah, 275. And this, too complicated, of course, I don't remember, minus 476 meters. Right. Okay, so now let me write again in a nice form. D3 equals to minus 275 I hat minus, 476 j hat. The rest is very simple. So in order to find these components of D, we just need to add all x components and all y components. Yeah. Cosine 60 is 1 over 2, right? So D3 is 550. So it's a 275. No, it's 500 over 550 over. No, I can divide by two numbers. I'm comfortable still with that. All right. So now then the next step. So D vector total, which is of course D1 plus D2 plus D3, and so I will add immediately 620 plus 381. So let me 620 plus 381 plus, not plus, yeah, let me write plus minus 275. And two brackets must be, two parentheses must be closed. You know that important fundamental law about parentheses. If you open two parentheses, you have to close two parentheses, right? Conservation of brackets. So that's x component. And then add all y components. So plus 0 plus, minus 220. and then minus plus minus 476. Of course, units of meters. Okay, I will just look at my notes, the numbers. So D equals, if you add them all up, maybe I will write here units of meters. Again, if something not clear, let me know. So 726. Okay, maybe I had, and minus 696 j hat, and again units of meters. So these are the components of the net displacement. Does it make sense, pluses and minuses? X component is positive. Just based on the picture, right, it looks like our vector will be in the fourth quarter. So positive and negative, yeah, it's in the fourth quarter. So seems like correct. So, and now let's find the magnitude of this vector and the direction in order to exhaust the problem completely. So now magnitude of D. So what do we have to do? So we just need to find, so you know what, maybe I will draw it underneath. So essentially we found D, and this is our dx, and this is our dy. Just Pythagorean theorem must be used, right? So because we need to find essentially this hypotenuse if we know this side and that side, right? So Pythagorean theorem, nothing fancy. So we can get that d equals to square root of dx squared plus dy squared. Okay, again, I will use my notes. Number looks ugly. 1005.7 meters. Since we have what? Sig figs, it looks like 2 sig figs only. So it's essentially, it's 1,000 meters. But on the exam, if the question about adding numbers and it's written taking care of sig figs on level of uncertainty, a certain level of uncertainty, then of course you need to apply all those rules which we learned. But with the rest of the problem, sort of rule of thumb, if you have numbers in the problem, let's say with 2 sig figs or 3 sig figs, a similar number of sig figs must be in your final result, right? And if you will be off, slightly off, I'm not picky in that sense, right? But of course, if you have problem with numbers where 3 figs are given and you will give us 10 sig figs, that's a little bit too much. Of course, in that case, we would write something and subtract some points. Right? We should be reasonable. So, okay, let's say 1,005 meters, right? Of course, actually, it should be just 1,000 meters based on the level of uncertainty of our numbers. So now direction, the final question. Direction usually is measured from the positive x-axis and more convenient. So let's say I will introduce this angle phi. Right. And like we've done in the class, I usually use tangent, but you can use sine, cosine function, any function, because we have a hypotenuse, we know adjacent side, opposite side, so any function can be used. So, but anyway, I'm going to use tangent. So now it's a direction. Tangent of phi, it's a opposite ratio of an opposite side, which is y component, versus adjacent side, which is x component, right? So absolute value of dy divided by the absolute value of dx. So x and y components are given. I will just write down immediately the answer. So phi will be equal, where are the numbers? It's the last. 43.8 degrees, about 44. As I said, it's a little bit tedious, but that's normal when you work with vector quantities. And so far, quite often, I give problems about vectors on the exam, because from this point, physics 1, physics 2, vectors will be everywhere almost. So you have to be really, really comfortable. Physics 3 also occasionally, or maybe more than occasionally. Okay, any questions? Yeah. What do you mean on the plus x-axis? You mean how to present this final result? If the problem doesn't say, then it's up to you. You can convert into the conventional angle 360 minus what you found, or write that okay, actually in this case, yeah, I should have added. So of course 44 degrees below x-axis. Yeah, of course. Friday evening I usually blame in that case if I start making some silly mistakes. So of course below plus axis. So thanks for the question. Actually it's a crucial. Below plus x-axis, right? Otherwise, yeah, it's confusing. He was first. That was your question. Yeah. Add what? This piece of information. Very simple. According to the convention, which we discussed in the second or third class, angle theta, when you define direction of the vector, is measured by convention from plus x-axis in a counterclockwise direction, right? So like this. Or if a vector is here, then theta would be this one. If the vector were here, then theta would be that one, conventional. Right? So for example, for the vector d, conventional angle should be, not should be, is this one. This is conventional angle. But we found which angle? This phi, which is convenient. Because I don't like dealing with vectors which are larger, angles larger than 90 degrees. It's minor compulsion, right? But of course, in that case, if we use convenient angle, sometimes we need to add the words like this, right? Because in our case, vector d is in the fourth quarter, right? And we need to express it. Because if you leave your answer like that, everyone would understand that your vector is in the first quarter at 44 degrees from plus x-axis in the counterclockwise direction, right? So you'll just confuse people, and yeah. That's why those words must be added, or something like this. Yeah? It depends. If your vector here, and if you measure this angle, then of course it will be below minus x-axis. Or to the left from minus y, or something like that, right? So, or clockwise, counterclockwise from a certain axis, right? So just explain. Reasonable logical explanations. Okay, so now next, or more about the displacement, something simple. I think I should be able to fit it here, and then I will erase. So now, displacement. Let's imagine this situation. What? Yeah. Yeah, you can do that also. In this case, you would clarify, you would explain everything. Yeah, it's also possible. I forgot to tell about that. Imagine this situation. What if we pick y-axis and it's upward? And then we toss a ball. This one, right? Up, up, and then it goes down. And let's assume that initial position of the ball. Let's assume that this is 0. No, let me put 0 over here. So this is y equals 0. And so ball moves this way. So you throw it from this point, let's say y equals 1. Okay, I will use probably red for the trajectory. So this is the initial position of the ball. Then it goes up to 0.5 and then goes down to slightly out of scale. More than slightly. Right. And then it goes down to y equals -3. Let's assume it is in meters. So first your ball is at 0.1. You drop or you throw it. It goes to the 0.5 and then it goes down to -3. So this is the final point. So this is initial position, and this is the final essentially position. So what's the displacement? Displacement, you're saying 4 meters, right? Any other? 3. -3. What else? Any other options? -4. We're getting more negative. The amount of negativity in the classroom is growing. 12. You're a really positive person. Okay, so let's just refresh. What is a displacement? Again, you remember it's that quantity which has this boss's attitude. It says, I don't care how you traveled or what you did between your initial and the final point. Boss wanted to know only where you started and where you finished. How much of work you did or how much you sweated. He doesn't care or she doesn't care, right? So displacement, by definition, you take your final coordinate and subtract your initial coordinate. What the system did between those 2 points, displacement doesn't care. So in this case, according to this definition, y final minus y initial, because we have one-dimensional motion in the y direction, so what are we getting? So let me write displacement equals, so it's a y final minus y initial. What's the y final? -3. Okay, meters we assumed, right? Then initial point, 1. But there is a minus because we're subtracting. So it's a minus 1 meter. So as a result, displacement is -4, right? Like I think you said, right? -4. -4. And so what, again, displacement is a vector. So let me show it on the graph. So, okay, I use all the colors on the green left. So essentially displacement is this. So that is our displacement vector, which starts at the initial point and ends at the final point, right? Remember that. It's a displacement. But now if we ask what's the distance? Distance is a scalar number, right? Scalar quantity. No. That is kind of wrong. Under certain conditions, maybe it's possible, but those are special cases. No, distance, it's the length of the actual trip. All the corners, if you went there, it counts. If you went there, it also counts. Sort of distance is like your mother's attitudes. Who cares what you did and how much you actually covered or how much of work you've done, right? Doesn't have this boss's attitude where you were and where you are now, right? Oh, you poor thing, you work so hard, right? So here in this case, what's the total distance covered? So first it went up to 0.5. So, okay, let me write. So now it's a distance. Distance equal. So first it went from this point to that point. It's a 5 meters. We're just counting the total length of the total trajectory, let's say. So first it went up. What did I do wrong? It's 4, actually, not 5. Sorry, I forgot that it starts at point 1. So up 4 meters. So let me write. It's that part which, when it went up. Then from this point it went down from point 5 to point -3. So it means that now additional part 8 meters, right? 8 meters. So plus 8 meters, so it's on the way down. And we're getting that the distance is 12 meters. And that's what you said, right? So you confuse distance with the displacement, right? So it's just a by definition. Because quite often you want to have this boss's attitude and you want to describe what happened using displacement, but sometimes you want to know all the gory details, right? So in that case, you use this distance. So pretty much we introduce all possible all those quantities which we need to describe all possible situations around us, right? Okay, so you need to remember that because, yeah, quite often I give, of course, questions about these two quantities, and your confusions are very common. Right? So now I hope you're not going to make these mistakes, right? Distance and displacement, bosses, and your mom's attitude, if it helps. And again, so what does this minus means? It's a one-dimensional vector. It's a vector quantity, right? So minus just indicates that your displacement vector is point down in the negative y direction. Positive y direction is up, and this is down, right? Okay, I think it should be enough, right? So after this, you should be able to answer these questions reasonably easy. So now, okay, any questions? More? Okay, let me check if everything is rolling. Okay, this is good. This is also rolling. So now, next question will be conceptual. We're going to analyze a bunch of different graphs because I noticed that you guys have troubles connecting real physical situation with the graphs, x versus t, v versus t, velocity, and acceleration versus time. So let's look at some different situations, right? Because again, reading graphs will be everywhere. It doesn't matter where you're going to be. Physics, engineering, mathematics, right? You're going to plot tons of different graphs, right? Crazy graphs, three-dimensional, and of course, every time you should be able to connect with physical situation. And this is, of course, just the beginning. So, let me erase this. So now it will be question 2. When you start erasing large area, you feel like, you know, those vacuum cleaners which run randomly around the room cleaning. Feel like, why no one has invented something like this for the whiteboard? All right, 2. So a bunch of graphs. Okay, it's about translational motion. Let's discuss translational motion. Bunch of graphs. So I will leave some space over here in order to describe physical situation, and then underneath I will start drawing graphs. So let's say I have x versus time. Muscles memory, try to write x. And let's assume that we have this particular graph. So something like a parabola almost, with branches up. So x position versus time. Maybe let me reduce it. And so what? I want to, okay, let me call this, it's x2, yeah. And over here, x1. So I want to plot v versus time. No, first over here we will describe physical situation. Then we will plot velocity versus time. And then acceleration versus time also. So first, let's imagine what happens to real object in our real life. So all x information is in front of us. We just need to read carefully. So object, okay, let me introduce even first coordinate system. Let's assume that we have some object which moves along x-axis. So it's not a graph, it's just a some object moves back and forth along this straight line. Yeah. Motion. Translational motion, MOT. Okay, I was lazy to finish the word. Translational motion graph. So, and let's assume that this is 0, x equals 0. Again, guys, don't be confused. So here it's x versus time. Over here it's a time in this direction. But here it's just a physical situation. Some object moves back and forth. Right? And I introduce coordinate system x. Right? So now let's start looking. At initial moment of time over here, object is at x1, and x is largest out of all possible, right? So it means that somewhere object was here. All right, okay, let me use blue. So let's say this is x1, this one. And then what happens to that coordinate? It starts going down. So it means in which direction does the car move? In the negative of x direction, right? In the negative x direction, x is going down, right? So it means that, so our object moves this way, right? That is sort of displacement for now, let's say. Then, so it goes, it keeps going down, down, and then at certain moment, x stops. Right? It doesn't go any below than this x, x2. So it means that it will come, for example, to this point. Let's say this is x2, and that is the minimum x. And after that, objects x starts increasing. So it means that at this point, object turned around and started moving in the positive x direction. Now x increasing. So essentially, this is x2 is a turning point, and now object is coming back essentially to the initial point. Right? So that's what happens to x. Now let's try to understand, because it's not the full description. We don't know when the car, what happens to the velocity, right? Velocity increasing, was increasing, decreasing, what was happening to the velocity. So in order to get that information, we need to look at the slope of the graph. So what happens to the velocity? Now, first of all, from this point to that point, is velocity positive or negative? Negative, because the slope is negative, you see? Slope is negative, so over here velocity is negative. Let me show that. V is less than 0. Then what happens to the absolute value of that negative velocity? Is it increasing or is it decreasing? Absolute value. So first, increasing. Okay, absolute value. Not forget for a second that it's a negative. I just want to discuss what happens to the absolute value. Because what does it mean, negative velocity? It just means it moves in the negative x direction. All right? So then what happens to the absolute value of the velocity? Look at the slope. First, slope is kind of large. And then it's getting less steep, less steep, less steep. And eventually at this point, what's the slope? Velocity is 0. So what happens to the velocity? It's getting smaller and smaller and smaller and smaller. Sort of, okay, the car is slowing down to this point. So this velocity over here, v, okay, goes down. Okay, on this part of the curve. Then, so at this point, it's a turning point. And then what happens to the velocity? So first of all, velocity now is positive or negative? Now, of course, velocity is positive. Okay, let me show over here. So v now is positive. Again, positive, it means it's this part of the curve. It means it moves in the positive x direction, which we established in the first part. And what happens to that velocity in time? Increasing, right? Because again, look at the steepness of the curve. So here, there is no steepness. It's a horizontal line. Slope is 0. And then the curve is getting steeper and steeper and steeper. Slope increases, increases, and increases. So the car is speeding up, accelerates. So it speeds up. No, accelerates. So essentially, physical situation as a result. I know over here, I know the car wants to make a U-turn. So here it moves fast. Then, of course, you press on the brake. Of course, you slow it down, comes to the point, turning point, turns around, and then press on the gas, and you start accelerating. Right? So essentially, it's a turning point situation. Right? All right, turning point case. Right. Okay, so now let me plot the velocity eventually. So over here, it's a negative, and first it's a large. So it starts, let's say this is the moment of time when turning happens. So first, velocity is large in absolute value, but negative. Then it's getting smaller and smaller and smaller, slowing down, stop for a moment, turning point, and then it will continue with the positive velocity accelerating. So straight line. Again, we assume that it's a straight line because this is kind of, I cannot guarantee which curve I drew. Oh, approximately parabola. So just a straight line. And turning point, what's so special about turning point? At a turning point, velocity changes its sign. Here it's negative, here it's positive. Of course, between them, there must be 0, turning point. So now acceleration. Acceleration, since the slope is the same on v versus t graph, so acceleration is constant. And it's surprisingly, it's positive everywhere, right? It's positive. Acceleration is positive. Although over here it's kind of decelerating, but here it's accelerating. But acceleration is positive everywhere. So I can draw something like this. So it's a constant acceleration. Again, why acceleration is positive? Because acceleration, again, it's a vector. Positive and negative, it just indicates what's the direction of the acceleration vector. So when our car was over here, moving that way, slowing down, right? So what's the direction of acceleration? Velocity that way, but it's you're decelerating, so of course acceleration that way, opposite. Velocity that way, but it's going down, so acceleration this way. And this direction, it's a positive x direction. So that's why this acceleration up to this point is positive. Now, it turns around. Now, velocity that way. And the car accelerates. Acceleration, again, in the same direction like before the turning point, right? So this is the tricky part which can confuse you. Because it looks like here you're slowing down. Here you're accelerating, but in both cases, acceleration is the same, positive. Right? So because, again, positive and negative is just a direction. OK. So first situation. Now, let me look at another case. And the third case I will skip. You can look by yourself when I send you my notes. So now, second situation. So what if we have a graph like this? X versus time. And the graph is, oh, no, wrong color. Okay, you know what? Let me do better because I want to get a certain feature of the curve. Yeah. Okay, approximately like this. Okay, it's too steep. Let me reduce the steepness. Right. So x versus time. And let me also go down. So this will be, I know, x1. This will be x2. And again, first, I want to describe the physical situation, and then v and acceleration. So in a very similar way, let's discuss. What happens to x? So first of all, x is positive throughout the whole motion. So I can safely put over here somewhere x equals 0, because the whole motion will be on the right side of my x-axis. Right? So it starts with a small x, maybe somewhere over here. Let's call it x1. And then x increases. Then for a moment it stops increasing x, but then it will continue increasing still. So it means that it will be just a motion like this. So from point x1 to the point x2. From the first graph, we can get that information, but of course it's not a complete description, because at some point x increases faster, sometimes x increases slower. And in order to describe that part of the motion, we need to dive deeper into the velocity level, right? Because right now, by looking at this curve, tons of information is still missing. So let's reveal that information. So in order to do that, let's start discussing velocity. So, over here I didn't show v. Should I, okay, do it like this, t. Okay, velocity. Now, again, we just need to start looking at the slope. So what happens to the velocity from this point to that point? Velocity, positive or negative? Positive, because again, our curve is increasing, so this slope of the tangent line is positive from this point to that point. So velocity is positive. It means it moves in the positive x direction, which we observed. Then what happens to that velocity as it moves from this point to that point? Decreasing? Agree or disagree? What happens to the velocity as the car moves from this point to that point? What happens to the velocity? Is it increasing or decreasing? Decreasing, yeah, because the curve is getting less and less steep. So first over here, you see how steep the curve is, and then it's getting less and less and less and less and less steep. So it means that velocity, which is the slope of the tangent line, velocity is getting smaller. So it means that object, okay, the car is decelerating, right? Decelerating, and what happens at this point? It stops for a moment. Velocity is 0, right? Because on purpose, I drew it in such a way to show that this is the horizontal line. So at this point, v equals to 0. But let's compare with this case. You see over here, also velocity was 0 at this point. Let me emphasize that v was 0. It's a turning point. It stopped, turned around, and started moving in the opposite direction. But now what about this point? What happens at that point? It stopped again, like in the previous case. And what it does after? It will keep moving in the same direction. Because you see, now a velocity, is it positive or negative? Still positive. It is positive over here, it's positive over there. So it means the direction of the motion is still the same. But here, what happens to the velocity? Here, velocity was negative, and after that point, velocity is positive. So it changed the direction of motion, right? So over here, and as a result, I can plot. So this is, let's say, a certain moment of time. I connect these two graphs. So from here to there, velocity is positive, so above the t-axis, and it's getting smaller. So it will be something like this. And again, I assume it's a constant acceleration, so I'm drawing velocity as a straight line. And after this point, now velocity is still positive, so it's still above t-axis, but now it's increasing. You see, it's getting first 0 and then getting steeper, steeper, and steeper. almost like victory, right? So velocity. So now, what's the which physical situation? Over here, it's sort of like a turning point case. What is that? Okay, if we connect it to the driving, it's like a red sign, right? Red traffic light. So you drive over here, right? So then you notice that traffic light turns red. You press on the brake, you slow down, you stop for a moment. Then when it turns green, you will continue driving in the same direction. So it's a red light, traffic red light situation, right, essentially. Here it's a turning point, and that is a traffic red light situation, right? Red traffic light case. Let me write that down. So this is red traffic light case. Okay, and the final graph, acceleration. Let me plot it, but acceleration is, in this case, is easier. All right. Acceleration, positive or negative from this point to that point? Negative. Slope is negative. And of course, it's constant because it's a straight line, right? It doesn't matter where you measure the slope, this point, that point, slope is going to be the same. So acceleration is constant, and as you said, negative. So let's say negative, and let me connect all these graphs again with a straight line, because the same moment of time here, the same time here, the same time there. Right? So then over here, acceleration jumps from negative to positive, because now slope is positive, velocity is positive. Right? So now acceleration jumps and stays constant. Okay, that's how you should read and analyze. Again, I cannot give you a recipe, just stare and analyze what happens to x, then look at the slope, and then what is positive, negative, it means positive x direction, negative x direction, stuff like that. Also, I prepared case number 3, but it's very similar, so I'm going to skip that, and you can read it by yourself. Right? Okay, if you have questions, ask. Otherwise, I prepared another bunch of graphs, but now velocity versus time, because, okay, based on my experience, that's where quite often students have problems understanding. And again, we will connect with the physical situations. So now let me disconnect this. And now, what if I have these graphs? First of all, it's about object moving in the vertical direction in the presence of the gravitational force. Okay, acceleration due to gravity. We did not introduce forces in the presence of acceleration due to gravity. And I will point my y-axis. I can do better than this, I hope. Yeah, y-axis is upward. Right. And there's a ball moving somehow along the y-axis. Right. I cannot say how it moves, because we will have to, by looking at the graph, we'll have to describe what happens to the ball actually according to this or that graph. So that's why I just showed the line. Ball moves up and down, let's say, ball. Okay, and now a bunch of graphs. Let's start with this one. What if we have velocity versus time, and the graph behaves like this? You know what? Let me draw all the graphs first. And you can start thinking, and I will, in a couple of minutes, I will discuss it with you. So then second graph, again, velocity versus time. Let me lift t-axis slightly, so then it goes this way. Then let me draw it this way. So first it goes down, and then goes like this. And the last graph, all possible crazy situations. V versus time, and now it's this way. Whew. So this graph, let's start with the first one. And again, ball. So first, what happens to the velocity over here? It starts from 0. And first, velocity is positive. According to our coordinate system, it means ball starts from rest, from certain level, and moves up, accelerating. So how can it move accelerating in the upward direction? I don't know, maybe it has a jet engine, who knows, right? Fancy ball. So it starts from, let's say, from the bottom, and start like a launching pad, right? And start turn on the engine, and starts accelerating. So it accelerates, moves up, reaches maximum velocity. Then what happens after that? Velocity becomes still positive. Velocity is still positive, right? But it's going down. So it means what happens? So it first accelerated up to this point, increasing velocity, and after this point, it sounds like it just turned off the engine, that jet engine, right? And now it continues moving up, but now decelerating because of the acceleration due to gravity, right? I know the problematic situation with the rocket, right? So first it accelerated to a certain altitude, then something went wrong with the engine, and it continued flying up just because of the inertia, and decelerating because of the acceleration due to gravity, right? And then eventually velocity becomes 0, and it doesn't mean that it hits the ground. No, it actually reached the maximum altitude. First it was accelerating to this level. Now velocity is maximum, and after that it continued moving up, but now velocity is getting smaller and smaller and smaller. So at this point it reaches the maximum altitude. And after that, of course, we don't know what happens because it's not shown on the graph, right? You see? Now it's you need to look at the graph and imagine what happens, right? Because after this point, it's probably not very clear that it continued moving up. But according to this graph, that's what happens, right? See that? Okay, so now let me write something below. Sort of, it's a situation where jet engine. So over here, the jet engine was on, and over here now that jet engine is off. Decelerating because of the acceleration due to gravity. Great. Now this graph. Which motion of the ball happens over here, and according to this coordinate system? Initial velocity, yeah, I can see you showed it. So initial velocity is 0, and then after that velocity is negative, and that negative velocity in absolute value increases. So essentially negative, it means negative y direction. It's this situation. You just drop the ball, and negative velocity is negative, again negative according to the my chosen y-axis, and it's just accelerating in the negative y direction. Right? So this is just a ball, dropped ball. So this is dropped ball. Right? Now this case, another crazy situation. Actually, not that crazy. So first part, look, this part, the same like here, essentially, right? So essentially it means that I drop the ball. What happens at this moment of time? No, again, you're thinking in terms of space. Come on. Here, it's not x or y changed. It's velocity jumped. Velocity jumped. Essentially, so something happens over here, and now velocity becomes positive and large. And then it starts, velocity goes to 0. Essentially, it's a situation like this. If I drop the ball and there is a surface, ground, it hits the floor at this moment. And then what happens to the velocity? Velocity changed the direction. Now velocity is positive, and it's decreasing because it's decelerating. So this part, it's when ball bounces off the ground. So here the ball is on the way to hit the ground. Of course, during the hitting, it's when it collides with the ground, physics which we're going to discuss later. But right now we just want to discuss the motion. And this is the situation when the ball bounces off the ground. Right? And again, it's very common confusion when students see, okay, some gap, and they think that x changed. No, it's a velocity change. So don't be tempted and don't jump to those wrong conclusions. We are looking at the velocity. So this is the ball bounced off the ground. Ball bounced off the ground. Off floor. Right. Oi, what the hell happens in the last case? So let's start thinking. Yeah, first case exactly the same like over here. It's a dropping the ball. We drop the ball, right? And then after this, what happens? Velocity is still negative. Velocity is still negative. It means that it's still going down, right? But now velocity is not increasing in absolute value, being negative. Now it becomes less and less and less negative. The absolute value of the velocity is getting smaller. I can connect only with this situation. Let's assume that here, instead of the floor or the table, there is a, swimming pool. So now, if I drop the ball, so of course, first it moves like over here, like over there, just reaching the surface of the water, and then it gets into the water, and because of that buoyancy force or something, of course, now velocity will start getting smaller and smaller and smaller. Eventually, at some point, it will stop, right? So I just bunch of curves and try to connect with real possible situations, right? Okay, good. I think it should be enough. Just stare at the values, what happens to each parameter, and try to imagine what can happen. Good. If you don't have questions, if you have, ask. Now, you know what? Let's just quickly add and multiply a couple of numbers, taking care of that uncertainty and sig figs. Couple of examples very quickly, right, just to refresh. And then we will move to actually projectile motion and then rotational motion. Because this is, as I noticed, lots of troubles over here, reading graphs. You know what? What should I erase? Why not? Wait, I can call it number 3. But it should take like a few minutes. So let's just add a number. So let's calculate with correct number of significant figures or with the right level of uncertainty. Okay, so let's add these numbers. 1.53, whatever units, I don't care, plus 2.786 and plus 3.3. We need to calculate this. Let's assume this is, you measured 3 distances with different level of uncertainty, and you want to add them up, and you want to know where the accuracy is in the answer. So if you use your calculator, you will get something like this, 7.616. It's a calculator result. And of course, immediately I will cross it out because most likely it's not correct. So you remember, if you add or subtract numbers, you need to look at the level of uncertainty and find the weakest link based on the level of uncertainty. You just need to find the weakest link. So let's see, where uncertainty, you remember, according to the convention, it's all the time it is in the last digit of the number. Last digit, the second digit after the decimal point, Here the third digit after the decimal point. Here it's the first digit after the decimal point. Which number is the weakest link? Obviously the last one, the weakest link, with the number with the largest amount of uncertainty, the largest amount of error, right? So this is measured very accurately. This is a very diligent person measured. This is kind of a little bit less diligent. And this is a sloppy measurement, let's say. Of course, the sloppy measurements will kill all that accuracy of the other two guys, right? So this is the weakest link. This level of uncertainty, first digit after the decimal point, must be used in your final result. So let me write. So it's a least certain, certain, this number. So this level of uncertainty must be here. So uncertainty must be in the first digit after the decimal point. So now once you found out where the level of uncertainty should be, what should we do next? Round the number to that digit. Rounding, next digit is 2, so it means that less than 5, so it means that the rest of the digits can be just dropped, right? So we will get 7.6, right? So let me check. Yeah, 7.6. So we'll get approximately 7.6. Very simple. Again, but when you add or subtract, you just need to look at the level of uncertainty. If you multiply or divide, next question, you will have to look at sig figs. So now let's look at next example. Multiply, let's say 11.24 times 1.95. Again, if you use your calculator, you will get something like 21.92. But of course, immediately, most likely it will be wrong. I just cross it out. So now let's see what is the correct number. So now you need to look at significant figures. Again, here we were just looking at the uncertainty, level of uncertainty, now sig figs. Right. Sig figs, in the first number, 4, right? 4 sig figs. So over here, SF equals to 4. In the second digit number, SF equals 3. So which number is the weakest link? Obviously, the number with 3 sig figs, right? So it means that this number of sig figs must be in our final number. So it means that we need to keep only these 3 digits. Once we found out how many digits we must keep, the rest we need to round. Rounding, the next digit is 2, which is less than 5. So during the rounding procedure, it means we just need to trust that last digit. But if we had here, let's say, 6, and of course we would have to add 1 to this digit, and then it would lead another 1 to this digit. So it will be just 22.0, but in this case it's a 21.9. Again, let me check. Yeah, 21.9. So it will be approximately 21.9. Again, quite often I give a couple of examples of this type on the exam. But of course, for the rest of the problems, I'm usually not very picky in terms of this. I told you the rule of thumb. If you have a certain number of sig figs in the statement of the problem, keep the same number of sig figs in your answers, right? So, yeah. Look at that examples, those examples. Okay. Oui. I wish I had something. Let's say 0.06 times 10 to the power of, I don't know, 3 plus. I'm just making it up, so I have no idea what I'm getting. Let's say 5.1 times 10 to the power of 2 plus, I don't know, 3.12 times 10 to the power of 4. I have no idea what Okay, so first we need to rewrite it in such a way that all this 10 to the power of something will be exactly the same in all three terms. Right. So let me keep what? 10 to the power of 2. Yeah, let me 10 to the power of 2. So 10 to the power of 2 times. Over here, it will be 0.6, right? 0.6 times 10 to the power of 2, it's this, right? Am I right? Hold it. Yeah, it's correct. Right. Then, okay, nothing can be done with the second, 5.1, and then plus 312. Okay, right? And now, the same rule like here, because there's no level of uncertainty over here. So now we just need to apply this rule over here. So we need to look at the level of uncertainty of each of these numbers. So first digit after the decimal point, first digit after the decimal point, and the first digit before the decimal point. Which number is the weakest link? Of course, the last one, right? It's a very sloppy measurement relative to this and that, right? 2 orders of magnitude difference in terms of accuracy, right? So it means that uncertainty in the final answer must be determined by this number. Okay, let me try to add them if my mind wouldn't explode. 5.7, so it's a 317.7, right? So 317.7 times 10 to the power of 2. Of course, I will cross it out. And according to this, since this is the least certain, so it means that this level of uncertainty must be in the first digit before the decimal point. So, and again, rounding. So we have the next digit, a 7, which is larger than 5. Of course, it means that we need to add 1 to the previous digit. So it will be 318. So it will be approximately 318 times 10 to the power of 2. Okay? First step, pick some common 10 to the power of something. Right? Again, it doesn't matter. You can use this, you can use this, you can use something else, right? Common for the sake of convenience. And then after that, you just use the rule of adding numbers. Okay, so now the next problem will be somewhat long. All right, I will have to erase everything. Right. I will start here, erasing. So it will be number 4. Definitely there will be problems about ballistic, projectile motion, not ballistic. Why I keep saying ballistic? So it will be number 4. Okay, let me check all the gears. Still recording. I lost the cover of my antenna somewhere. Okay. So this physical situation, what's called archer, right? Who shoots arrows. So somebody shoot an arrow up in the air at, I think, 45 degrees from the ground level. And of course, ground is horizontal, so of course it will land, not of course, let's assume it lands again at the same level on the ground some distance away. So what is given? 45 degrees, and we only know the travel time. Let's say you shoot an arrow and you look at your watch. Let's say 5.4 seconds later, you can see it hit the ground. So using this information, we should be able to find initial velocity and then a bunch of other stuff. And we're going to find all those parameters using different ways of finding, different tricks. Right? Okay. So projectile motion, right? So the first problem is an arrow, right? Flying arrow. Every time, guys, before, at the very beginning, of course, I ask you to draw physical situation because it helps tremendously. I cannot imagine solving the problem without sketching the situation. Students quite often do that, but of course with lots of mistakes, right? So I'm encouraging, draw. I keep telling the same to upper and the graduate level students, physics majors, graduate even students. Pictures helps, they help. So let me sketch the situation. So this is the full ground. And the arrow, okay, we assume it goes from the ground. Pretty much we assume that the height of the person is negligibly small, let's say. Right, so the trajectory is going to be like this. Parabola, all the time. It doesn't matter how you throw something near the surface of the Earth, every time it's going to be a parabola. It can be shown mathematically. So this is an arrow flying. So initial point, final point. And so what is given? Okay, I will write down later what is given. So first step, after sketching the situation, you need to choose the coordinate system. You cannot continue solving problem without choosing the coordinate system and the origin. It's up to you where to position the origin. You can position it here, point x-axis this way, y-axis that way. Okay, or you can position it over here. Also, it's not wrong, but it's not the most convenient. Right? So there's no such thing as a wrong coordinate system. There are less convenient and more convenient. So in this case, I think the most convenient, of course, at the initial position of the arrow. So let me draw it. So that is my y-axis, and this will be my x-axis. So now, once I did this, now I can start writing down what is actually given, because it's good to have everything in front of our eyes in order to start analyzing which equation is better to use. So I will probably start writing over here. So here there will be column for x values, and here for the values in the y direction. Okay, let's start with acceleration. So what can we know about acceleration in the x direction? 0. We neglect air resistance. Acceleration is 0. Then acceleration in the y direction. Let's make a decision immediately about the sign, positive or negative. Of course, acceleration is that way. We cannot change that. We all know. Positive or negative? Yes, according to the positive y direction, that vector is negative, right? G is downward, negative. So we need to model it. We model it with our theory, model physical situations. So we're converting physical situations with our numbers, signs, and so on. So minus G. Then initial velocity, we have nothing. We don't know. We'll have to find it. So we don't know that. Then final x, we don't know final. Actually, which way I label it? I think, okay, let me label this final point as point B and initial point, no, the top point as point A. Right. So this will be x B. Not given. And what do we know about the y coordinate of the final point? Y coordinate of the final point? 0. It's a ground level. Again, 0 according to my chosen coordinate system. It started from 0. Actually, I should have written y first, not, and then yb. Okay, let me write first. Y naught equals 0 and yb equals also 0. It started from the ground and it hits the ground. Then x naught, of course, 0, and x final, we don't know. So what else do we know? We know information about the time. Time, okay, let me separate it like this. Right. And so time equals to 5.4 seconds. So that's what is given. And according to question A, part A, you know what, let me, right underneath. So we need to find initial velocity, right? Yeah, initial velocity of the arrow in the unit vector notation. Unit vector notation, you remember, I hat, j hat. So we need to write in that. So essentially, we need to find x component of the initial velocity and y component of the initial velocity. That's the first part. So we need to find v naught x and v naught y. And let me show on the picture what we actually want to find. So this is the initial velocity. Again, you remember it's tangent to the trajectory. We discussed that. So this is the initial velocity v naught. And this is our v naught x. And this is v sub 0 y. So we need to find that. Not much is given, so what can be done? So I'm offering to use 3 methods of finding initial velocities over here. So what is good about this problem relative to the problems which we solved in our recitation classes? Symmetry, right? The graph is symmetrical relative to this point, this line. So what is happening over here on the way up? It's almost exactly the same like what happens on the way down, right? So if we have the total travel time, 5.4, do you know the travel time from this point to point A? Half of that, right? Half of that. So as a result, my first method of finding this suggests, what if we try to use this point as the final point in our equations, remembering that, of course, the travel time is the half of the total traveling time. And I think we should be able to handle this. Okay, so let me, you know what, let me write something. Row 1, first method. So, and let me write, so point A is the final point. What do I mean by the final point? You remember, every time in all these problems, we usually use some point as initial, usually it's this one. And then we decide which point is going to be final for this equation, this. It can be sometimes the top, sometimes the bottom over here. It depends on the situation. So in this case, I decided to use the maximum point as my final point. Right? And now, what is so special about that maximum point? There is a unique feature of that maximum point. Which one? Guys, we have two-dimensional motion. Every time we need to specify which velocity, because if you set velocity, immediately my brain, okay, I'm no physics to some extent. And immediately I think about the total velocity, magnitude of the total velocity, right? And it's not, total velocity is not 0 at that point. So you need to specify. Of course, I understand what you mean, but can you make correct statement? Y component of the velocity at point A is 0. X component is not 0, right? X component is still the same like over here. You remember the property of the X component of the velocity. It stays the same throughout the whole motion, and even at the top. So the total velocity at that point is not going to be 0. So Y component of the velocity at point A is negative. Let me show that. So over here, V naught Y is 0. But of course, V naught, okay, Y naught, it's A Y. Sorry, guys. Which way I label it? A Y is 0. But velocity X component equals to the X component of the initial velocity. Right? So, but I want to use this equation for point A. So, look, this velocity is 0, as he just said, right? Then this velocity we need to find. It's one of our unknowns. And then travel time, it's a half of the total travel time. And acceleration due to gravity, of course, we know. So from this equation, we should be able to find initial y component of the initial velocity. See that? Okay, let's do it. Equation number 1. So it's a v ay equals to v naught 0 minus gt. You know what? Let me label this time as b. It's a total travel time. You see point B? Because now I need to divide that by 2. So TB over 2. Right. And over here, let me use the symmetry. Okay, so this is 0. This is our unknown. And time, we know acceleration due to gravity, everyone knows. So if you solve it for v naught 0, you will get, okay, I will write down the answer. Why I keep writing 0y? A y equals to, okay, gt. We need to find 0 initial velocity, v naught y. Yeah, I was correct. So it will be equal to GTB over 2. Right. Okay, you can plug numbers because everything is given. And the answer is 26.46. It's a velocity, just meters per second. Now, can we find x component? Another piece which I said in words, but I didn't write on the whiteboard. I didn't give you the angle. I said that it's at 45 degrees. The arrow was shot. So this angle is 45 degrees. Right. So over here, let me write theta equals to 45 degrees. Okay. So now, of course, I can ask the question. So we found this component. We know this angle. So we can find x component. Using tangent function. Tangent of this angle, it's opposite versus adjacent, right? So we can find x component easily. So now, tangent of 45 degrees equals to v naught y versus v naught x. In both velocities are positive, so we can just drop the absolute sign of absolute values. So tangent of 45 degrees, 1. 1 tangent of 45 degrees is 1. So v naught x, okay, tangent of 45 degrees, let me write underneath, it's 1. So it is equal to v naught y equals to 2646 meters per second. Okay, so now we can write in a vector form v naught v naught equals to 2646 I hat plus 2646 j hat. Yeah, probably doesn't make sense to keep 4 sig figs, round it to 3 sig figs. It's fine. So now it's one way. Now, second method. Just explore everything possible. Again, using the symmetry. Let me ask you. What if I draw over here a final velocity? VB. And just draw. Of course, we don't know that velocity. But what if I decompose? Okay, you know this x is annoying. Let me extend it. Okay, x. This will be our x component, VBX, and this will be VBY. Again, using the symmetry, what can you say about the magnitude of the y component at point B, y component of the velocity at point B, and y component of the velocity at the initial point. What can you say about this magnitude and that magnitude? Symmetry. They must be the same. They must be the same. So in terms of energy, we can sort of discuss like this. Let's say first it starts over here. So first velocity is large, and then it goes, it becomes smaller and smaller and smaller and smaller, and at the maximum point, y component of the velocity is 0. Then now it has some kind of potential energy, and now it starts returning, turning back to the kinetic energy. Now it starts going down, and the y component of the velocity becomes larger back, larger and larger and larger and larger. And at this point, magnitude only of the y component over here is exactly the same as magnitude of the y component over there. And it's not about only final points. You can take any, for example, this altitude, and look at this point and that point. Y component here, of course, it's up, and y component over there, which is down. Magnitude's the same. We can use that fact to solve this problem using this method, right? Okay, so let me write it down. Again, symmetry. I can write that v not a y absolute value equals to the absolute value of v by. Why absolute value? Because their directions are opposite. On the way up, it's up. On the way down, it's down. Directions are different, right? But absolute values must be the same. You can use this trick sometimes to simplify some analysis solutions, right? Okay, so now if we have this, then we should be able, again, to use this equation. But now final point, of course, B. Now B is our final point. It's not like here. I use point A as the final point. So now equation 1, so which is v by equals to v not y minus gt. And now the total travel time, because now we use the whole parabola, right, the whole motion. And this is equals to minus v not y. Magnitude's the same, directions are opposite. We need to take care of the directions, right? So we need to show that, right? So this is down, this is up. Right. Okay, so now we have the same and the same, but here is minus. So if I move this, okay, if you're confused, let me rewrite it. V not y equals to minus v not y minus gtb. Of course, we need to move to the same side. Of course, it will be minus, so it will be minus 2 v not y equals to minus gtb. Of course, minuses can be dropped because they're on both sides of the equation, and we're getting the same answer, right? So v not y equals to gtb divided by 2. Look, here, there, the same answer. So usually there are more than one option to, method. Yeah, minus it. Yeah, now this is correct. So of course you move to that side, it's negative. Yeah, sorry. Long day. Again, I usually blame Friday evening. So, and of course after this, exactly the same. And then the same. And then the same. The rest is the same. The rest is the same. So what else can be done? The last option which can be used using, in the first these two methods, we use this equation. Now we can use this equation also. Most likely you would pick the last option. The last, let me use the third method. So the equation now I'm going to use y equals to y naught plus v naught yt. And I'm going to use, again, point B as the last point. Because we know the final y coordinate of the final point. And minus 1 over 2 gtb squared. So, y coordinate 0. Initial y coordinate also 0. Right? And we're getting, we need to find this. So let's solve it. TB can be cancelled on both. Okay, because now over here we have zeros. Let me write. So from here we can get, this is minus, right? So 0 equals to v naught y tb minus gtb squared over 2. So that's, if I move this to that side, it will be with minus. Minus, minus on both sides can be dropped. And we can solve it for v naught y. V naught y will be equal to, t gets cancelled, gt sub b over 2. The same answer like previous two methods, right? So g times time divided by 2. And then the rest, of course, the same tangent and then the same. So I'm just trying to exhaust all possible situations. Yeah? Okay, it depends for your convenience. No, for you, according to your method, which point you're planning to use as the final point. You remember this? All these equations allows us to predict the future. And let's say we know something in the future, and you want to use this result. So in the first method, I decided, okay, I want to apply these equations when this is my final point. Of course, I divided the time by 2. But now in this third method, in order to use this equation, I see, okay, I have some information about the y coordinate at the final point. So let me use point B as my final point. Again, it depends what is given, what you want to find, and which equation you want to use. Sometimes you can use, if you want, you can use, if you have some information, if you had some information at this point, maybe you would pick that point as your final point. But of course, we don't have any information at that point, so of course it doesn't make to use it. Doesn't make point to use it. Yeah. The rest, okay, I thought I pronounced it. So basically, the rest is tangent in order to find x component. The rest is the same. Right? And now, of course, after this also, the rest you just need to use tangent in order to find x component. Okay. V-O-Y. This is definitely O. This is not B. Right? Yeah, but yeah, sometimes if I start running faster, right, it becomes difficult to read. Okay, so now another. So that was part A. Now part B. I think we need to find coordinates of this maximum point, y coordinate. Yeah, we need to find y max. So we need to find that y max, which is essentially y at point A. So now, speaking of your question, now if we want to find something at point A, of course we will use that point as our final point using these equations, because in these equations, any point can be used as the final point, any point can be used as initial point. It depends on the problem, what is given and what needs to be found, right? These are quite, let's say, universal within this acceleration equals constant. Right? So maximum point. Now, let's start looking at the equations again. The first equation, it doesn't have y, so it's not an option. Let's look at this. This is our what we need to find. Y naught is 0. V naught we just found. V naught y. Travel time to point A, we also know it's a half of the total travel time. Then G and T. Okay, we can use equation number 2. direct application. But also at the same time, I think this equation can also be used. This is, as we discussed, it's 0 at point A, y component. This we found, this is of course given. Ya, that's what we need to find. Y at point A, and this is 0. Also, equation number 3 can also be used. But whenever I see squares, I don't like that. Although here we also have square. But you just, okay, I would probably use, okay, any of those. Actually, I solved both using both equations. So let me write both. So now point A is the final point. So now Ya equals to y naught plus v naught y tb over 2 half of the time. I'm just rewriting this equation. I decided first to use this equation, right? And then minus 1 over 2 g, and the time now, of course, it's a tb over 2 to the power of 2. And again, this is our unknown, right? So that's what we need to find. So just need to plug number. This is 0, right? So we found this. We know this time. We know that time. Everything is given. So let me write the answer. Right. So it will be 35.72 meters. Of course, we can round it to 36 meters. Or, let me write, or we can use that equation of v ay squared equals to v naught y squared. What? Yeah, where's the equation? Minus 2g ya minus y naught. So this is 0, and this is our unknown. And again, this is also 0. Of course, yeah, you can solve it. So it's a ya will be equal to v naught y squared over 2g. Right. Yeah. Okay, so the same, 36, of course, approximately 36 meters. So you see, quite often there are more than one methods of solving this or answering this or that question. Yeah. Because A is our final point, right? So, and the travel time to that point is 2.7 seconds, right? So the final question, part C, we actually need to find the range. In this problem, yeah, you can use that famous range formula which students adore so much. I don't know why, but every time students try to use that range formula, but that range formula can be used only in the cases like this, when initial point and the final point are at exactly the same level. Only in that case, range can be used. And that's why on the formula sheet, you will never find that range formula, because I'm actually kind of against even giving that to you. I never used it. Everything can be solved using these equations. Everything is here. That range formula, of course, can be derived, and it's only correct for special situations. And students try to use it almost everywhere it's possible, everywhere where it's possible or not possible, right? So that formula is not going to be given. So now range x, b. And now the final point is point B again, because the question is about finding distance to point B, right? And of course, the equation, there's only one equation for that. X naught is 0, that's what we need to find, and this we found also in first part. So, and travel time, of course, now 5.4. So it will be xb equals to x naught plus v naught x times tb. And of course, x naught is 0. Right. So again, if you plug numbers, you will get 142.9 meters, so approximately 143 meters. It's not the record. Some of the final exams, they were about 4.5 hours in physics 2, I remember. Of course, after that, I feel usually completely exhausted. Okay, any more questions? Can you hear me at the back? Okay, good. I didn't want to use the speakers because I just don't want to wear 2 microphones. It looks too weird. Okay, I prepared another problem, flying ball, but now essentially the situation is like this. Over here, there is a building, and you throw the ball from some height, okay, 2 meters, let's say I am 2 meters. And you throw the ball to the building, which is also has some height. And you need to find also a bunch of different parameters. So let me for now skip it. Of course, I will send you my notes, and this problem will be attached. So you can look by yourself, right? It's similar to, you remember that problem about Romeo and Juliet, right? Something like this, right? So you can, over here also only there is one tricky part. No, but I explained to you. Okay, so I think you should be able to understand. All right, because you're getting tired. So now let's move to rotational motion. So first conceptual question similar to what we discussed before that problem. You remember those graphs, how to read graphs. And then rotational kinematics, and that will be the end of the day. So it probably another half an hour or maybe 40 minutes. Can I start erasing? So that will be number 5. So now 5 and rotational motion. And again, my experience in the previous years, lots of problems with rotational kinematic equations. All right, so here with this better situation, but with those lots of mess. Right? So, okay, let's review rotational motion. So graphs. So first, let me put the first bullet, some kind of, and theta, whatever units, radians, degrees, revolutions, I don't care, versus time. Again, whatever units of time, doesn't matter. And graph looks like this. So first goes up, then it goes down, and then it stays constant. That's just completely arbitrary situation. And of course, we will have to discuss what actually happens to the system. So let's say this is some angle theta 1. Then over here, let's say it's theta 2, and time, of course. So first, we need to discuss physical situation, and then we need to plot omega, angular velocity, and then, if it's possible, we can also say something about angular acceleration. So now omega, in the middle, let me draw it somewhere like this. So rotating system, essentially, we can imagine it's a point mass, for example, spinning around the circle, around, for example, this axis of rotation, or maybe it's just some rigid object disk, and you point a mark, some dot, and it's spinning, right? Probably this is easier to imagine, right? So we need to discuss what happens based on this graph, what happens to this dot. So first, theta is, okay, so let me, although we don't use x and y coordinate system, but every time, usually I prefer to draw it in, on the picture. It helps. It helps to see from which direction we measure angle and so on. Although we don't use it, but it's very helpful. At least I find it. Right. Okay, so I assume that theta naught equals to 0, and this is our initial point. Because every time you can adjust your coordinate system x and y and make theta 0 equals 0, so it's not a big deal. So initial point at t equals 0. Object, the dot, is at this point. Then theta is positive. It means what's the direction of rotation of the object? Counterclockwise. We assume that this is conventional angle, so counterclockwise. So it means that from this point from this angle, from this angle, point moves, right? So from this angle to that angle, theta 1, it increases linearly. And so let's assume that it goes this way, and let's say this is our angle theta 1. It's possible it made a few revolutions even, but I don't want to draw that. It's too complicated, right? So every time use some angle which is you can easily show. So that's this part. Then at this point, it stops for a moment, angle stops changing for a moment, and then angle starts going down. So it means that at this point, it turns around, or just it stops and you start spinning a disk in the opposite direction, essentially, right? So now it goes this way, theta decreases, and it doesn't decrease to the 0, so it decreases to some angle theta 2. Okay, let me show that. For example, let's say this is angle theta 2. So it means that this point moves to this level. So trajectory, first it moves up. Okay, not up. Counterclockwise, stops for a moment, and then disk gets turned back by some angle. So that's physical situation. But again, we see what happens to the angle, but it's not the full description of the motion, because we also need to know sometimes theta increases faster, sometimes theta increases slower, sometimes maybe something else happens with theta in time. In order to describe that, we need to dive to the next level of the velocity level, angular velocity level, right? So an angular velocity, how can we get information from the graphs? It's like here, we just need to look at the slope of the graph. Yeah, so, and of course, what happens at theta 2? It stops turning, right? So now there is no any movement, right? So now after, when it reaches point theta 2, motion stops. Okay, rotation stops. And angle doesn't change as time goes by. So now information about the velocity. What can you say about velocity on that part of the graph? Positive, negative? Positive. Slope is positive. What does it mean, omega positive? Because it's a pseudo vector, but anyway, it has a direction, right? According to the rule, convention. Omega is positive, it means it spins in a counterclockwise direction. So let me, yeah, counterclockwise direction this way from your point of view. So CCW. So omega is positive, so it means that CCW, right? Counterclockwise. But omega stays constant, right? Because slope is exactly the same, right? There is no acceleration. So you see, slope is the same throughout the whole time from this point to that point, that moment. right? So omega is positive and constant, so it means that let me connect these two graphs because they are, it's time. So this point and that point essentially the same moment of time, right? So from this point to that point, omega positive and constant. So now next, when it goes down, theta goes down, so it means that omega now obviously is negative. So omega is negative. It means that it spins in a clockwise direction, which we observed, right? And theta changes at the same rate, so omega is constant, right? So slope is exactly the same. It's negative. So velocity jumps to some negative value, and then it stays constant all the way to that point. And after that, theta stays constant. It means angular velocity is 0. Okay? So now it jumps to 0 and stays 0. Actually, this description is easier than those one-dimensional changes in x. Right. So it looks like based on your responses, did you get it? I think it's not a rocket science, right? So the second example, I prepared 2 examples to practice. I think you should be able to read it by yourself, right? If you, or do you want me to look at the second example? No? Okay. He's definitely saying, no, don't do that. Okay. 1% democracy. I saw his head moving. Right. Okay. And why I sort of agreed on that, because let's solve a couple of problems about these rotational kinematic equations, right? So usually I don't give any complicated situations, but again, based on my experience, it's very problematic usually for students, although idea is very similar between translational kinematic equations and rotational. Yeah, I want. Okay, you know what? I can fit it, so I don't want to erase. I like have a long whiteboards, like in classical mechanics theoretical courses. If I have a long whiteboard, I can start at one angle, and I usually finish by the end of the class. I reaches the other side of the whiteboard, because then you can easily compare stuff. You can see, you see what we've done over there. Now we're getting something slightly different, so it's much convenient to discuss the cases. So I hate when the whiteboard is very small. So rotational kinematic equations. Rotational kinematic equations. So let me first discuss physical situation. Car engine, automobile engine, slows down from initial angular velocity to the final angular velocity, given numbers, in a certain moment of time. We will have to find angular acceleration and the number of revolutions of the engine over that stretch of time. Okay, let me show it like this. So we have a, okay, it's a problem number 6 first. Problem number 6, and so it's a car engine, let's say. Let's call it this way. So you know what, how should I show it? Okay, omega naught equals to, should I call it? Yeah. What's the number? 3,500 RPM. You engineers, I don't have to explain to you what is RPM. Physicists usually don't use RPMs, right? We like radians per second. That's our units. But you guys practical, right? So revolutions per minute, of course. Then this decelerates. And the final omega, which I label it omega 1, but essentially it's a final, right? Final equals to what? 1,200. Again, RPM, revolutions per minute. And this happens over the stretch of time, so which is t1 minus t0, and you remember t0 is usually 0. It happens over, no, it's too complicated. Let me write. So this is t0 equals 0, and then it happens over the period of time. No, you know what? Let me do it this way. Trying to find more efficient way. So it happens at 2.5 seconds. Okay. So first column in initial values, second column the final values. Right? So this deceleration happens in 2.5 seconds. So we need to find angular acceleration, and of course over this stretch of time the engine is going to complete some number of rotations, revolutions. So we need to find that number of revolutions. So part A, we need to find angular acceleration. Right? So I think I gave you everything. Yeah. Do we have to adjust units in order to start? Definitely we will have to apply some of these rotational kinematic equations. Of course, we're going to assume one small assumption we have to make. Which assumption? Yeah. We don't have any information about acceleration. Maybe in real life it's not constant. But if it's not constant, of course, it would be illegal to use these equations. In order to practice, let's assume acceleration is constant. And most of the time it's a reasonable approximation, right? So we're going to assume that alpha is constant. Assume alpha is constant. Okay, now back to the units. Do we have to adjust our units? Because, yeah, we will have to most likely use either this equation or maybe that. We will discuss equations. So, do we have to make some adjustments to our units? Time is given in seconds. Our angular velocity is given in revolutions per minute. So we have to either change units of time or change units of our angular velocity. I prefer to change units of the angular velocity. At the end, I know I feel more comfortable applying these equations, just dealing with normal units. Okay, nothing wrong with minutes, but I prefer to have seconds. Okay, so let me change RPMs to RPS, revolutions per second. Although there is no such thing as RPS, right? But why not? So adjust units. So first, let's adjust units. So omega naught, it's 3,500 revs per minute. So we just need to get rid of minutes. Very simple. In 1 minute, there are 60 seconds. So just divide it by 60. No way. Let me look at my units. I mean, at my notes. 35, it's 58.33 revs per second. And the same we can do with omega 1. Omega 1, it's 1,200 revs per minute. And the same 1 minute over 60 seconds. Guys, you should be very comfortable converting, for example, revolutions per radians, or degrees into radians, or degrees into the revolutions, right? So in order to convert revolutions to radians, you need to remember that in one revolution there are 2 pi radians, complete circle, 2 pi radians, right? Or 360 degrees in one revolution, right? Yeah. I don't think that I gave that in the formula sheet. Actually, I never thought. Now you gave me this idea. Now I need to think about this. But usually no one so far has ever asked me to actually give. Everyone knows that 2 pi radians, 1 revolution. Right? But if you ask me on the exam, of course, I would most likely give you, right? So, not most likely, I would definitely give you that. So the answer is 20 revolutions per second. Okay, so now we have nice units. So we need to find what? Angular acceleration. Now let's start thinking which equation the best. Omega final given, omega initial given, travel time, piece of cake, right? So travel time is given, so we can find acceleration from the equation number 1. And the units already adjusted. Because if you try to use RPM and mass it with seconds, of course, you will get a big mass in terms of units, right? No one is going to like it, right? So then this is, we need to find what? Acceleration. We don't know the final angle, right? So pretty much this is no for now. Then this final, we know initial given. We need to find the same problem, or theta. Theta not is 0, but we don't know theta final, right? So it's a part B. So pretty much at this point, only one equation number 1. There are no options. Only one method which can be applied to find angular acceleration. So equation 1. So omega 1 equals to omega naught plus alpha t1. I paused for a second for a reason. Because I thought, can you guess? Okay, not guess. I don't know, gut's feeling. Acceleration, positive or negative, are going to be? Yeah, it decelerates, right? It decelerates, so most likely it's going to be negative. So we will get that minus automatically. First, I thought, should I put that minus manually? But no, it doesn't make sense. So we're supposed to get that minus automatically. So alpha equals to omega 1 minus omega naught divided by t1. Everything is given. Plug numbers, calculate, right? And units are correct. Or maybe let me write that down. So it's 58.33. I skip units, divided by 20, divided by 2.5 seconds. Okay, I will just write units at the end. So here will be revolutions per units. Revolutions per what? Square seconds. Square seconds, right? So if you calculate, what did I get? Two. No. Something is fishy. Something is fishy. No. I think I messed up. So omega 1, 20. Okay, yeah, because I'm not getting negative number. So you see, omega 1 is 20. I just get confused with the numbers. So it's a 20 minus 58.33. Okay, this is correct. So, and of course now the answer is minus 15.3 revs per square seconds. So negative, yeah, makes sense. So second, I think the second question is obvious because everything is given and known now except for how many, what's the angle? Number of revolutions of the angle. So now I think we need to find theta. Yeah. So now we need to find theta 1. Number of revolutions. Number of revs. So again, start staring at the equations. Theta is here and there. So from this, that's what we need to find. Theta naught is 0. Again, we adjust coordinate system to make it 0, not a big deal. Omega naught given. Travel time given. Alpha we just found. Time is given. So just plug and calculate the number. Then this can be also, I think, used. Omega 1 is given, final omega. Initial also given. Alpha we just found. And this is our unknown, and this is 0. Equation 2, equation 3 can be used easily, right? But still, of course, I would prefer to use equation 1, because over here I'll have to take a square roots. No, actually both equations are reasonably simple. Both. So which I used, okay, I use second equation. Right, so equation 2. So theta 1 equals to theta naught, which is 0, plus omega naught T1. I will put plus 1 over 2 alpha, alpha t squared because alpha is negative, so minus is in our value of acceleration. So plus 1 over 2 alpha T1, T1, yeah, squared. Yeah. Okay, everything is known now. Something was given, the rest we found. So if you plug numbers, you will get 97 point, okay, I rounded 9 revs, which is approximately 98 revolutions. I keep plugging numbers. Just following the advice of students. I remember after my first semester in my evaluations, one student wrote, don't plug numbers, we can do that easily. So after that, I usually follow that advice. Right? Unless there are some tricky situations where I need to show something, but usually, okay. So now the last problem. Yeah, it will take probably 10 minutes. And we'll call it today because you're getting tired and we're getting closer to the end. Again, you see logic for these equations and for those equations extremely similar, right? So don't panic. So it's on the exam. So let me erase this. So it will be number 7. Again, if you think that it's something disconnected from real life, try to imagine. I know astronomers probably do this all the time, right? Observing some galaxies spiraling, moving, spinning, right? So it's everywhere, right? Plus, you have all the time superposition of two motions, translational plus rotational. So you have to be really, really comfortable with all this stuff. Right? So we have some wheel. First initial angular velocity is given 18 radians per second. Then it starts slowing down at a certain rate, 2 radians per square seconds. Essentially, acceleration is given. And we need to find how many revolutions will it have turned through by the time it stops. So first it has some initial angular velocity, then there is some maybe friction force, it starts decelerating, and of course the final angular velocity will be of course 0, it stops. So we need to find number of revolutions between the initial moment of time and the moment of time when it stops. So physical situation. So number 7, and this is the spinning wheel. Okay, spinning disc, whatever. Okay, I will use C, not K. Yeah, skip this. There is another problem, but you can look at that by yourself, right? T equals 0. It's a T naught, right? So what do we know? Omega naught equals to 18 radians per second. Then it slows down. And at the rate, angular acceleration equals to 2 radians per square second. And omega final, it stops, 0, right? So read the problem. Sometimes you just need to read the problem and convert into numbers. So it stops. Yeah. The distance square. Before we start, actually, maybe I should write what we need to find. What do we have to find? Number of revolutions. We need to find theta final. Number of revolutions. Revs. I want to discuss acceleration. We obviously will have to use one of these equations. Again, we will discuss which one. And definitely there will be acceleration. So what do we have to say about our acceleration for those equations? Okay, let me give a chance. Yeah. Great. Very actually important statement. Acceleration is constant, so it's legal to use the equations, right? So of course, great. Next thing, I see that you. What else do we know about acceleration? The object is slowing down. We need to show that we have to show that information somehow, insert that information somehow into our equations. So what do we have to make with our acceleration? Negative. We have to make it negative. In order to use in our equations, we need to put minus in front. That's why you see I wrote absolute value of alpha, because right now it's also, we have that number and the fact that object is slowing down. So now, in order to start using those equations, we need to make that statement. So since it slows down, so we need to write that alpha equals minus 2 radians per square seconds. Now we're all set, I think all set for the to start using equations. So now let's start looking at the equations actually. The first one is obviously no, because it doesn't have an angle. We need to find angle theta. Number of revolutions, it's angle. That's what we need to find. This is 0 again. We assume that it's easily achievable. Omega naught, given. Travel time, we don't have travel time. So equation number 2 is also not good. Again, you can combine probably equation number 1 and equation number 2, and it will work, but you will have to make one additional or maybe 2 additional steps. Not bad, but not the most efficient way, right, of solving problems. So, but you remember for those cases, look, information about the time essentially not given. T not equal 0, it's obviously, right? So it's not information about time. So information about time is not given. The question is not about time. It's a clear indication that most likely equation number 3 will be the most convenient equation to use to solve the problem, right? So equation number 3, let's analyze it. Omega final 0. Omega, yeah, it's given. Alpha is given. That's what we need to find. Theta naught is 0. Equation number 3, right? So equation 3. So omega final squared equals to omega naught squared. Then minus 2 alpha. You know what? Okay, of course, there are 2 ways. You can either write plus and then use the value which is negative at the end, or you can show it explicitly in the equation. So it's up to you. I decided to show that minus explicitly in the equation, right? So, but of course, don't use that minus twice, right? So here I showed that minus, and then, of course, after this, use the absolute value of acceleration. So it's a, let me even show that this minus appears over here so that you wouldn't get confused. Right? And so our theta final minus theta naught, and of course, theta naught is 0. We can easily achieve that. So pretty much now piece of cake. So this is our question. This goes to that side. Okay, let me do it step by step. Omega final squared minus omega naught squared equals minus 2 alpha theta final. And angle will be equal. Okay, I will move this minus to that side and change the order of these omegas. It will be omega naught squared minus omega final squared divided by 2 alpha. You know, I can just show absolute value of alpha since I showed minus explicitly. So now I put an absolute value of alpha so that you wouldn't have temptation to use that minus one more time. So in terms of units, everything is fine. Here we have rads per second. Here we have rads per second squared. So we don't have to make any additional adjustments. Right. So the answer. Plus omega final is 0. Phew, it's much easier. So omega final is 0. Right. So omega naught, so it's 18 rads per second squared divided by 2 times 2 radians per square seconds. So you can calculate and you will get 13.5 revs. No. First, it's in radians, of course, 81 radians. Yeah, in physics or mathematicians, we used radians quite often. But if you tell me 81 radians, is it a lot or not? That's confusing, right? So, of course, at the end of the day, of course, we will also prefer to convert it into the revolutions, right? Much more convenient. So let's convert. All right, so theta final equals to 81 rads. So we need to get rid of radians. So we need to remember that 1 revolution is 2 pi radians. So radians must be downstairs in the denominator. 2 pi rads, it's a 1 rev. So, okay, I will again use my notes. What's the answer? 13.5 revolutions. Right. So you see, it's, I would say even these problems about rotational kinematic equations, I would say it's even a little bit simpler than those projectile motion. Because here it's truly one-dimensional, but there you have 2 dimensions and you need to somehow juggle them together. Of course, you can also find the time between this and that moment. You can easily find time because now you have this is 0, this is given, acceleration given, so you can find also the travel time, right, easily. Right. So now travel time. Okay, just want to exhaust the problem. So which one I used? Equation 1. Omega final equals to omega naught. Then minus alpha absolute value times t. T is given. Yeah, we need to find that. We need to find it. Right. So you can easily find the travel time. So of course this is 0 again. So the travel time or rotation time, 9 seconds. Yeah, it's 18 divided by 2. I can calculate without my notes. So it will be right, omega naught divided by absolute value of acceleration, so it's 18 rads per second divided by 2 rads per square seconds. It will be 9 seconds. Wait, that's an ugly second. Whew, enough, because I feel that you're getting tired. But yeah, 2 hours, 40 minutes, that's approximately what I predicted, try to predict.